Welcome to this deep dive. Today we're tackling the F test.
Ah, yes, the F test.
Ever wondered if, adding all that complexity to your data analysis model is actually worth it?
Hmm.
Or if the differences you're seeing are maybe just, well, random noise?
Right. Those are exactly the kinds of questions it helps with.
So the F test seems like a really powerful tool for that. Our mission today is basically to demystify it a bit, show how it works for comparing models and understanding variances.
Exactly. And when we talk about comparing models, the F test is fundamentally asking, does adding more variables significantly improve how well our model explains the data?
Okay.
It looks at the balance, really, the variance our model captures versus what's left over unexplained.
Like, does adding extra detail actually make the picture clearer or just busier?
Precisely. Is the added complexity paying off in terms of explanatory power?
Okay, so it's about measuring that
Right.
payoff. Now, this test uses something called the F distribution. What's the deal with that?
Well, the F distribution, at its core, it comes from the ratio of two variances, specifically two chi-squared distributions divided by their degrees of freedom.
Okay, chi squared, degrees of freedom.
Yeah, and the key things to know are its two parameters, degrees of freedom for the numerator and degrees of freedom for the denominator. Think of degrees of freedom as like the number of independent pieces of information you have for estimating each variance.
Right, so it's about how much solid information you're basing that comparison on.
Okay.
We see the F test pop up in ANOVA and regression analysis quite a bit. How does it function there?
Ah, yes. Crucial applications. In ANOVA analysis of variance, the F test is, well, central. It compares the average values across several groups at once.
To see if any of the groups are significantly different.
Exactly. It tests the null hypothesis that all group means are equal. In regression, it assesses the overall significance of the entire model.
The whole model.
Yes. Do all your predictor variables taken together explain a significant amount of the variation in your outcome variable? Or is the whole model kind of useless?
Gotcha. So in both cases, it's testing if the patterns we see are likely real, not just chance. And you mentioned the F ratio earlier. What's that telling us?
The F ratio is the test statistic. It's literally the ratio. Variance between the groups, or variance explained by the regression model divided by the variance within the groups, or the unexplained variance, the error.
Okay, so explain variance over unexplained variance.
Basically, yes. A larger F ratio means the variation between groups, the signal, is large compared to the variation within groups, the noise.
So a bigger ratio equals stronger evidence against the null hypothesis, like stronger evidence something interesting is going on.
That's the idea. Stronger evidence that the differences or the model's explanatory power are statistically significant.
Makes sense. Now, those degrees of freedom you mentioned,
Yeah.
how do we actually figure those out for ANOVA and regression?
Right. So for ANOVA, the numerator degrees of freedom, that's the number of groups minus 1. Simple enough.
Okay.
The denominator is the total number of observations across all groups minus the number of groups.
Total data points minus groups. Got it. And for regression?
For regression, the numerator degrees of freedom is just the number of predictor variables you've included in the model.
Ah, the number of things you're using to predict.
Exactly. And the denominator degrees of freedom is the total number of observations minus the number of predictors minus one more.
Okay, observations minus predictors minus 1. It clearly depends on the model structure and data size.
Yeah.
Now, are there rules, assumptions we need for the F-test results to be, trustworthy?
Oh, absolutely. Like most statistical tests, it relies on some key assumptions. First, independence of observations. Each data point should be independent.
Standard stuff.
Yep. Second, normality. The data within each group for ANOVA or the residuals in regression should ideally be normally distributed.
Morality, okay.
And third, homogeneity of variances. This means the variance should be roughly equal across the different groups or across the range of predicted values in regression. We sometimes call this homostaticity.
Right, equal spread. What happens if these are, way off?
Well, violations, especially of normality and equal variances, can make the F-test less reliable. Your p-value might be inaccurate.
Good to know. Keep those assumptions in check. Now, I've also heard the F-test used for comparing nested models. What's that about?
Ah, nested models. That's when you have, say, a simpler model and then a more complex model that includes all the variables from the simpler one, plus some new ones.
So one model is sort of contained within the other.
Exactly. The F-test can then specifically compare these two models. It tells you if adding those extra variables in the complex model gives you a statistically significant improvement in fit over the simpler one.
Ah, so it helps decide if adding those extra predictors, those bells and whistles, is actually doing anything meaningful.
Precisely. It's a way to justify adding complexity.
But what if we don't have that equal variance thing? What if we have heteroscedasticity?
Yeah, that can be a problem. Unequal variances, or heteroscedasticity, can mess with the F-test. Specifically, it often inflates the type I error rate.
Meaning you might reject the null hypothesis incorrectly, find a significant effect when there isn't one.
That's the risk, yes. You might think your model is significant or groups are different when it's really the unequal variances causing issues. There are alternative tests or corrections sometimes used in these cases.
Okay, so caution is needed there. Can we also just use the F-test directly to, like, test if variances themselves are equal between groups?
Yes, you actually can. The simplest form of the F-test is just the ratio of two sample variances. You can use it to test the null hypothesis that two populations have equal variances.
Cool.
It can be extended to more than two groups as well, like Bartlett's test, which uses an F approximation. However, this direct test for variances is actually very sensitive to the normality assumption.
More sensitive than when using it in an ANOVA.
Generally, yes. So if your data isn't very normally distributed, using an F-test just to compare variances might not be the best choice. Other tests, like Levine's test, are often preferred because they're more robust to non-normality.
Interesting nuance. Okay, last thing, the F distribution itself. It looks kind of skewed, doesn't it? To the right.
It is, yes. It's always right skewed. And the reason is simple. It's a ratio of variances.
And variances can't be negative.
Exactly. Variances are squared values, so they're always non-negative. The ratio of two non-negative numbers is also non-negative, starting at 0 and stretching out to the right. There's no left tail dipping into negative numbers.
So that skewness, does it affect how we interpret the results? The p-values?
It mainly means we're almost always interested in the upper tail of the distribution. Large F values, far out in that right tail, indicate significance. We need to account for that skewness when determining critical values or interpreting p-values. It's not symmetric like a 2 distribution or a normal distribution.
Right, that makes sense. So wrapping up, the F-test is clearly a very versatile tool. Comparing means in ANOVA, checking overall model significance and regression, even comparing variances directly or assessing nested models.
Absolutely. It's all about that core principle. Comparing a measure of explained variance to a measure of unexplained variance. But, as we discussed, understanding the assumption's independence, normality, equal variances, and its limitations, like sensitivity to heteroscedasticity, is really crucial for using it correctly.
Definitely. Know the tool, know its limits. The key takeaway seems to be understanding that ratio of signal to noise, or explained to unexplained variation.
That's the heart of it. Get a feel for that ratio and you'll understand what the F-test is telling you.
So a final thought for you listening. Next time you're looking at comparisons or model results, try thinking in terms of that ratio. How much of what you're seeing is likely a real pattern versus just background randomness? The F-test gives us a formal way to ask that, but the principle applies much more broadly. Thanks for this deep dive.